Hi everyone. This is the solutions for the review number 3, for exam number 3, midterm number 3. Let's take a look at number 1. A 50-foot rope is tied to the top of a flagpole and anchored to the ground some distance away from the base of the flagpole. If the rope makes a 20-degree angle with the ground, find the height of the flagpole. With a question like this, I suggest by starting with a picture. So we have our flagpole. Here's the ground. We have a 50-foot rope. And that 50-foot rope, so let's put in 50 feet here, that 50-foot rope makes a 20-degree angle with the ground. And we're being asked for the height of the flagpole. So we can call that whatever we want. I will call it X. We have this angle here, 20 degrees. We know that this length here is 50 feet. This length is X, that's what we want to determine. So we know the hypotenuse. We want to know the opposite side. So we recognize that the trigonometric ratio, which connects the hypotenuse and the opposite side, is sine. Sine is opposite over hypotenuse. So in this case, sine of 20 degrees is equal to X over 50 feet. So we can solve for X. X is equal to 50 feet times sine of 20 degrees. And now it's calculator time. 50, we put sine of 20 degrees. We want to make sure that our calculator is set in degrees, since that's what we're using here. So sine of 20 degrees is about 0.342. And if we work this all out, we get that this is approximately 17 feet. So this length right here is approximately 17 feet. Let's take a look at number 2. So we have 3 cities, A, B, and C at the vertices of a triangle. The distance between city A and B is 100 miles. The distance between A and C is 200 miles. And the angle between those 2 line segments is 100 degrees. So again, let's draw ourselves a picture. So I'll put city A right here. I'll put city B right here. And that is supposed to be 100 miles. I'll put city C over here. And this is supposed to be 200 miles. And this angle right here is supposed to be 100 degrees. So let's finish our triangle right here. So we're supposed to find the distance between cities B and C. The third side of this triangle is not a right angle triangle. We know that when we're working in a non-right angle triangle, we have as tools the law of sines and the law of cosines. So let's go ahead and put a length in here. We are trying to find X. We're trying to find the length of that third side. We know that when we have one angle and 2 sides and we're trying to work out the third side, that's the law of cosines. So let's go ahead and write the law of cosines in as far as this triangle goes. So X squared equals this side squared, so 100 squared plus 200 squared minus 2 times 100 times 200 cosine of 100 degrees. Hopefully you can see that all. So X squared is equal to 100 squared, that's 10,000, plus 200 squared, that's 40,000. You add those together, you get 50,000, minus 2 times 100 times 200, so minus 40,000. And we'll need our calculator to compute compute cosine of 100 degrees. That's about negative 0.174. And if we do our computation right here, we end up with X squared is approximately equal to 56,960. Taking the square roots of both sides, we have X is approximately equal to 238. That might be a little bit too much accuracy. Let's make it 240 miles. Again, law of cosines. We know that this side squared is equal to this side squared plus this side squared minus 2 times that side, cosine of the angle in between. In both of these problems, there were units in the question. We put units in our answer. All right, let's move on to number 3. So 3a asks us to sketch 2 to the power negative x. So starting with 2 to the power x, we know what that looks like. It crosses the y-axis at 1. It goes through the point 1, 2. Approaches the x-axis asymptotically over here. A typical exponential curve growing to the right, that's y equals 2 to the x. Replacing x with minus x, we know that that's a flip over the y-axis. So 2 to the minus x, y equals 2 to the power minus x, is the same curve but flipped over the y-axis. So there we are, there's part A. Part B is y equals 1/2 to the x. Now, in light of what we've already done, this is going to be pretty straightforward. So y equals 1/2 to the x. 1/2 is the same thing as 2 to the minus 1. 2 to the minus 1 is 1 over 2 to the 1, or 1/2. And 2 to the minus 1 to the x, when you raise a power to a power, you just multiply exponents. So that's 2 to the minus x. So it turns out that the answer to part B is exactly the same as the answer to part A. We already have the graph on the blackboard. Let's take a look at C. Y equals 1 minus e to the x. So let's start off with y equals e to the x. We know that curve fairly well. It again crosses the y-axis at 1. It goes to the point 1 comma e. So y equals e to the x is right here. Let's draw y equals minus e to the x. Y equals minus e to the x. We put the minus sign in front of the whole curve. We know that this is just the curve flipped upside down. So same curve but flipped upside down. Now y equals one minus e to the x. That's the same thing as minus e to the x plus 1. It's the same curve. So it's that this curve shifted up 1 unit. So we'll shift it up 1 unit. Oops, it's supposed to be horizontal. So that curve looks very much like this. So y equals 1 minus e to the x looks like that. So there is C. And now D, natural log of x, that's a curve that we should know well. This is just the e to the x curve, reflected over the line y equals x, so we know it crosses the x-axis at 1. This is one of the ones we should have committed to memory. Y equals natural log of x. And in part E, part E, we're taking a look at y equals the natural log of x minus 1. We're subtracting 1 directly from the x. We know that that is a horizontal change. Horizontal changes are opposite to the expected direction. So this is just a shift of the curve 1 unit to the right. So instead of approaching the y-axis asymptotically and crossing at 1, it approaches x equals 1 asymptotically, crosses at 2. And there we go. All right. On to number 4. We're given that 2 measurements are taken of the same amount of radioactive carbon-14. So this is a problem in radioactive decay, 1 century apart. The amount of carbon-14 measured in the second sample is 98.7% of the amount of carbon-14 measured in the first sample. So let's define some variables. Let's let T be time in years. Let's let M be the mass of the sample. In grams. And these are 2 variables. I'm not told how much mass there is originally, so I'm just going to make up a constant. Sometimes in class we called it B. You can call it B. I'm going to call it M sub 0, the mass at time 0. And this is the initial mass. This is not a variable. This is a constant. So we're talking about radioactive decay here. That's exponential decay. So we know that M is equal to M naught A to the T. If you called this B, it would be B A to the T. Just a different letter. Okay, so in the first part, we're supposed to find the half-life of carbon-14. So how long does it take for a sample to decrease to half the mass? So we will set the mass equal to half of the original mass. Let's plug that in. So 1/2 M naught equals M naught A to the T. So when is the weight of the sample equal to half of what you started with? This is what you started with. When is it equal to half? So we're going to solve for T. The first thing we're going to do, we have an M naught on both sides. We can cancel that out. We can divide both sides by M naught. So we have 1/2. Oh, I'm sorry. I should have put in, not only am I supposed to set M equal to 1/2 M naught, but I have to